EI over L squared. Can someone tell me what's so unique about this formula in terms of structure analysis? I want you to reflect back when you're doing year 1 physics and when you're doing 2P. What is so unique about this formula? Anyone? What is stress equal to? Force divided by area. Yes or no? Right? Or force equal to stress times by area. What is so unique about this formula is, what is the pi doing down there? Have you seen a structure question that has pi? Yes or no? Never. We do calculate when it's circle, but we never had a structure question that's pi. Okay. Any idea what is I equal? So over there, all of you know what is pi, yes or no? 3.141592654. What is E? Make a guess. Yes. Young's modulus. What is L? Yes. Length of the beam. What is I? Yes. Second moment of area. Not moment of inertia, it's not dynamics. So when you start folding, what are we changing? Anyone? The shape. When you change the shape in that formula, what are we changing? What? I. For this case, the length did not what? The length did not change. Okay? The length did not. So I'm still folding. And folding is known as what? Anyone? What is folding? I know it's a stupid question, okay? But what is folding? Folding is also a what? A mechanical engineering problem, which is known as manufacturing. That's why you take 3CO3. Yes or no? Length is the same. Material is the what? It's the same. Cross-sectional area change. Did the area change? Area is still the same. But what changed? The second moment of what? Area change. So for this case, the second moment of area, is it bigger or smaller than what we have just folded? Smaller. Okay, this is what? Bigger. That is why for this case, when I put my wallet down, the whole thing will just what? There's no stability. Or there is no what? Stiffness. So when I come to this paper, because I've changed my second moment of area, what happens? Yes. This is how we analyze buckling. That is why when you see the formula, you have a what? You have a what over there? Anyone? You have a second moment of what? You have a second moment of area. My wallet weighs nothing because the wife took away all the money. Hey, you have to know that every single cent you earn as a husband all go to the wife. Are we clear? Okay? Don't keep a single cent. Money for men is evil. Now, this is where is at the age of what? Coupling, I mean, at the age of collapse. Okay, I want you to focus what will happen when it's collapsed. So this is heavier. If you were to focus on this end is going to bounce what? Outwards. Okay, so if I were to just bounce it, okay, you can't see it properly down here because it's holding. It's going to have a what? This sort of bellowing shape. Are we clear? That's where you see what? Buckling. I'm clear. Now, can someone tell me what is so unique about how I'm loading this structure? Come on, speak up. What is so unique? Just shout out what can you see about this structure? What type of loading is this? Anyone can tell me? Excel, what type of Excel loading? You're right, it's Excel, but what sort of Excel loading? Yes, it's only under what? Compression. So, i.e., buckling analysis you only need to carry out buckling when the structure is under what? Compression. If I were to give you a question that's under tension, and when you do buckling, you know what I'll do to you? I'll give you 0 immediately. Are we clear? So a structure like this, under compression, then you need to carry out what? Buckling analysis. Okay. Now, so I'm going to write this out. Don't worry. I know sometimes when I speak, I forget to write. Try to forget that. So what we realize, so this is the general formula. I'll show you the formula. We're going to spend like 3 hours to derive this formula. Okay. Not 3 hours, half an hour, not 3 hours. Okay, I'm just kidding. Right. So we know that buckling only occurs when structure are under compression axial loading only. Okay, so then that's where you have to focus on buckling analysis. So there are 2 types of buckling. Okay, there are 2 types of buckling. One, we call it centric, and the other one, the second one, we call it what? Eccentric. Have you all seen this term before? Yes or no? When Dr. Koshi taught you guys in what? Bending moment. Are we clear? In bending stress, you have centric and you have what? Eccentric. And the meaning is exactly the same. Okay, so I'll write down here these terms were also used in bending or stresses, normal stresses, induced, or normal stresses induced by bending moment. Okay, so our sketch centric. Okay, so in centric, so this is our structure. I'll draw it thin. Okay, and then this is our centroid. So I'll label this. This is our centroid. Now remember, I'm going to tell you this. Centroid is not necessarily always equal to neutral axis. I will highlight this into your mind first. I repeat again, the centroid is not equal to neutral axis. What's the neutral axis? So neutral axis is based on what? It's based on stress field. You're right. When stress is equal to 0. What's the centroid? How you get a centroid? Well done. This is based on what? Geometry. So do not assume that the centroid is always equal to its what? Neutral axis. Sometimes it's true. Most of the time it's what? It's not. Are we clear? Good. Right. So on the left-hand side, we have centric. And on the right-hand side, we have eccentric. So I'll take the same diagram. So very similar, like bending. And if I will have my transformation, this is X and this is Y. And if it's under centric buckling, the load will exactly act on where? Act on the centroid. Okay. Eccentric bending, you will see what? An offset. Okay. And this offset, you can see this distance from here to here. I'm just going to call it B. So now you see the difference between centric and eccentric buckling. Straightforward. So we have a set of formulas that we're going to apply for centric buckling. Okay, we have to derive a different set of formula again for eccentric buckling. But the way to derive the formula is very similar. Okay, so let's start from something simple first. Question from anyone so far? Are we okay? We're good, right? So from here, I'm going to bring you guys back to stiffness again. Okay, so the question now is, how does mechanical properties relate to the stiffness of a structure? Okay, the term over here is stiffness. A lot of times when I carry out this demonstration, a lot of times the audience will say this paper is not able to hold this pencil case. It's because there is not enough what? Stiffness. Now that's not true. This is because it is what? Buckling. Whereas for this case, the term used to say, oh, this paper is stiffer. We have to be really, really careful with the term used down here. Okay, so let's look at how we define stiffness. Okay, so if we have now a structure now, the structure is fixed at one end. Okay, and then I'm going to use green. This is my centroid. Right? And then our structure over here will have a certain geometry. This geometry will be known as our L0. And then we put our structure. We are going to focus on compression. The next structure on the right-hand side. This is exaggerated. This one has been shortened. Position of the centroid. This same structure has been shortened. And this is because now we have a load over here. And the load over here, I'll call it dy. Okay. So I'm going to sketch my transformation. This is my x and this is my y. What you see when you plot this out, you'll see now if we plot our stress strain curve out, oh no, stress strain curve. right? And then over here, back to the diagram,